All right, let's take a look at number 18, which is our first fluids problem. And what we have here is we have a U-shaped tube. First, there's some water poured into it. The two ends here are open, so we pour the water in. And now on over here on this side, we pour in the oil carefully so that when it fills in there, it doesn't mix with the water. And we're going to end up with something that looks like this. We'll have an interface between the water and oil here. They're not mixing. And on one side, we'll have this column of water, and on the other side, we'll have our column of oil. And so what other information is given? Well, we were given the height of the column of water here. We do know the density of water. All right, we can look that. Well, it's on our formula sheet, or we probably should just know that it's 1,000 kilograms per cubic meter, standard units. And the density of the oil is given here at 600. So, how are we going to do this? Really, the first piece of information that we need to work with here is actually a tiny bit of an approximation, but it should be quite valid for us. And that is, we need to think about what is the pressure at this interface here between the oil and the air. And the air here, it's open to the outside. World, and so what's the pressure outside? Well, 1 atmosphere. We'll consider it to be 1 atmosphere here. And so the pressure at that point is 1 atmosphere, atmospheric pressure. Now, what about the pressure at this interface right here? It's also touching the air, which is open to the outside world, and so we're also going to say that is 1 atmosphere as well. Now, here's where it's a tiny bit of an approximation, is that, we're going to see that this is a few centimeters. The picture may not be drawn to scale, but there's a number of centimeters here that this column is lower. Now, air is a fluid, and we know that as you go down in any fluid, the pressure increases. But when we go down a few centimeters in air has about 1/800th the density of water. And so the increase in pressure when we descend in air is very, very minimal in this case. So we're going to consider these two pressures to be the same, and there's actually one more point where we're going to consider the pressure to be the same, and that's going to be at this interface right down here at the bottom. And that should make some sense because the pressure on both sides of that interface between the oil and water, they need to be the same. If the pressure from the oil on the left side here was larger, then it would push the interface, would push that some of the water out of the way this way, and vice versa. If this interface between the water and oil stays there, the pressure on either side, right here in the water and right here in the oil, the pressures of those points have to be the same. Now, both of these, the pressure here is going to be larger than 1 atmosphere because in order to get from, say, here down to here, we had to descend in this fluid, the oil. And similarly, we've had to descend in our water. And so the only equation we're going to use here, we're going to be applying is that the increase in pressure as we descend inside this fluid is going to be the density of the fluid that we're descending in times G and times the depth that we descend. And so that increase in pressure, the pressure here above 1 atmosphere, should be the same whether I descend over on this side in the water or on this side in the oil. And so the result that we're going to get here by setting those two equal rho GH for oil has to equal rho GH for the water. We don't even have to approximate G in this case because we can just divide through. And at this point, we know 3 of these numbers. We know the density of the water and the oil, and we know the depth here of the water. And so we should be able to solve for the depth of the oil here, and we will get C 0.67 when we plug in those numbers.